Welcome. In today's module, we'll be discussing basic chemistry. In particular, we'll be looking at the structure of atoms. And you might be wondering why we're going to be studying chemistry in a biology class. And the reason is that when you look at the makeup of organisms and certainly the physiology of organisms, that all traces back to chemical reactions. And so it's important to have a basic understanding of some chemistry. So, what is chemistry? Well, chemistry studies the properties and interactions of the elementary particles of matter and the atoms and molecules they form. So we need to have an understanding of what matter is, and matter is anything that has mass and volume. Mass is a measure of the substance of something, and when gravity acts on mass, that's what generates weight. So here on Earth, we look at mass and weight as being the same thing. And then volume then would be the space occupied by a substance. Now, we're going to be considering three states of matter: solids, liquids, and gases. And in the case of a solid, the atoms and molecules will be in a fixed position. They really can't move from one place to another. In both liquids and gases, particles collide and move, and the difference would be the density of the two. So in liquids, the particles are moving around and colliding, but they're more dense. In gases, there's more space between them, and they disseminate and have, produce a gaseous state. Now, there's another state of matter called plasma that we will not be considering in this class. And so when you superheat matter, it is possible to strip the electrons from the nuclei. And this is an electrically neutral state of matter. But again, it's well beyond anything that we're going to be considering in here. All right, so when we get back to matter, then we're going to be considering elements. And elements are so-called pure substances that cannot be purified into simpler forms using chemical methods. And so when I talk about hydrogen, oxygen, carbon, nitrogen, sulfur, and so on, I'll be talking about elements. And the basic unit of an element is the atom. And elements are composed of like atoms. And so I'll be defining what that is in just a few minutes. All right, so let's get to the structure of an atom then. So when we look at an atom then, there are, again, these elementary particles, and we're really just going to be considering three particles. One of those would be protons. So protons have a positive charge and a mass of approximately 1 Dalton. And we find the protons in what is essentially the center of the atom, which we call the nucleus. Now, another particle that we find in the nucleus is the neutron. The neutron is a neutral particle, also with a mass of approximately 1 Dalton. And then orbiting in shells around the nucleus are much smaller particles which carry a negative charge. These are the electrons. And they have a mass of approximately 1/1800th of a Dalton. So when we look at the mass of an atom then, what we're really considering is the mass of the nucleus. And when we look at these diagrams of atoms, they're certainly not to scale. So for example, the nucleus of an atom is only about 1/100,000th of the diameter of the atom. And that would be comparable to a fly in the middle of a football field. So again, keep that in mind that this is certainly not to scale. So again, we're not going to be using really realistic examples, but again, we'll be looking at nuclear structure, protons and neutrons. Normally, the electrons really are forming a cloud around the nucleus, although we're going to be representing them as having specific structure and concentric rings around the nucleus. Now, also, protons and neutrons have no electromagnetic attraction, and so what holds the nucleus together is a force, a gravity-like force known as the strong force. And then electrons are held in their orbitals partly by electromagnetic attraction with the protons of the nucleus, but that's not enough to keep them in their shells or orbits. So there's an additional gravity-like force known as weak force, which helps keep the electrons in place. Now, the elements are organized in a so-called periodic table, and I would encourage you to download a periodic table and print one out that has both atomic numbers and atomic masses. This one that I'm using only has atomic numbers. And when you look at a periodic table, as you work from left to right, you'll notice that numbers get bigger. So hydrogen is element number 1, helium element number 2, lithium number 3, beryllium number 4, and so on. And then also you'll notice that there are specific arrangements vertically as well. And so I'll come back and talk about the significance of the vertical arrangements later. What I would want to point out right now, though, is that the atomic number does tell us something about the elements. Essentially, it tells us how many protons are in the nucleus. So the atomic number tells us the number of protons in the nucleus of an atom. And I'll come back to that in a second too. So when we look at the periodic tables, you notice there are little boxes there. And each box then typically has both the atomic number and the atomic mass. And so the smaller number will be the atomic number, the larger number will be the atomic mass. So as I just mentioned, if we're looking at this element chlorine, Cl is the symbol for the element. Chlorine is atomic element number 17, so that means it has 17 protons in the nucleus. And the nucleus has a mass of approximately 35, and so we're just going to be rounding off the mass. Now, again, atomic number tells us the number of protons in the nucleus. The atomic mass, again, is telling us the approximate mass of the atom. But if you think back, the mass of a proton is 1 Dalton. The mass of a neutron is 1 Dalton. So if we round off the atomic mass to a whole number, what that's also telling us is the approximate number of particles in the nucleus of that atom. Because again, electrons have an insignificant mass, about 1/1800th of a Dalton. So the mass number, the atomic mass then, when we round that off, is going to tell us the number of protons and neutrons in the nucleus of the atom. So if we know the atomic number, and we know the atomic mass then, we know the number of protons in the nucleus, and we will also be able to figure out the number of neutrons by taking the atomic mass and subtracting the atomic number. So let's look at a couple of examples, starting with the chlorine that we just talked about. So again, if we round off the atomic mass to 35, subtract the atomic number, that's going to tell us that there are 18 protons in that nucleus. So 17 protons, 18 neutrons, I should say, in that nucleus. So let's look at some other examples. So in the case of hydrogen, hydrogen has a mass of 1. Its atomic number is 1. So if we subtract 1 from 1, what that's going to tell us is that there is only a single proton in the nucleus. That's what makes it hydrogen, and 0 neutrons. Element number 39, or excuse me, element number 19, which is potassium. That's telling us it has 19 protons. There are 39 particles altogether in the nucleus. So the atomic mass is 39, so 39 minus 19 is 20. So there are 20 neutrons in the nucleus of that atom. Copper, element number 29, so that's again the atomic number, so that's the number of protons. The mass is 64. 64 minus 29 will give us 35 neutrons in the nucleus. So as long as you know the atomic number and the atomic mass, you should then be able to determine the number of protons in the nucleus and the number of neutrons in the nucleus. Now, as it turns out, there are different versions of elements, and we refer to these as isotopes. So isotopes are atoms of an element with variable numbers of neutrons. So they're different versions of an element. But as long as they have the same number of protons, then they are so-called like atoms. So again, let's look at some examples. The most common form or isotope of hydrogen is hydrogen 1. It has a mass of 1, and its atomic number is 1, so that's what defines the element. The atomic number defines the element. So since its atomic number is 1, that means it has 1 proton in the nucleus. If we subtract 1 from 1, we get 0, so no neutrons in the nucleus. And this is a non-radioactive substance, by the way, and I'll come back to that in a second. Now there's another version of hydrogen, hydrogen 2. It's also called deuterium. It has a mass of 2. It's still hydrogen because it has a single proton, so it would still have atomic number 1, and that means it would have a single proton in the nucleus. But if we now subtract 2 minus 1, it differs from hydrogen 1 in that there's not only 1 proton, but 1 neutron in that nucleus, and this is a radioactive version of hydrogen. Hydrogen 3 is a form of hydrogen with a mass of 3. It's also called tritium. Since it's hydrogen, the atomic number is 1, meaning it has 1 proton. So it's the number of protons that defines an element and gives it its characteristics ultimately. And so again, in this case, there would be 1 proton, 2 neutrons, and this also is a radioactive form of hydrogen. So there are 3 isotopes of hydrogen that we find out there. One version that has no neutrons in the nucleus, one that has 1 neutron in the nucleus, and one that has 2 neutrons in the nucleus. Then also we can look at carbon as another example. So there are 3 isotopes of carbon, carbon 12, 13, and 14. Again, they differ by the mass of the atoms. They're all carbon because they all have 6 protons. And so they would differ then by the number of neutrons in the nucleus. And carbon-12 is a non-radioactive form, and carbon-13 and 14 are radioactive forms. So what is radiation then? What does that mean? Well, one thing I should tell you about radiation is that another term for radioactive isotopes is that they're described as being unstable. And so if something is unstable, like if this building were unstable, for example, you wouldn't feel very comfortable here. It would mean essentially that it could fall apart. And so that's the same concept in radiation or radioactivity. The combination of protons and neutrons in some atoms upsets the strong force in a way that the atom cannot maintain its structure or hold in all of the energy. So that particular atom then will begin to lose particles and lose energy. So there's some different types of radiation. One type is alpha radiation. Alpha radiation is where the nucleus spits out 2 protons and 2 neutrons. Now, if a nucleus does that, of course, it's no longer the same element. If it loses 2 protons, it's not the same element anymore because it will have a different number of protons in the nucleus. Beta radiation is composed of electrons. So again, in some situations, atoms cannot hang on to their electrons. Those are emitted. That's beta radiation. Neutron radiation would be the loss of neutrons. And then there are certain types of electromagnetic radiation. Electromagnetic radiation would be very, very tiny particles called photons that move in a wave-like manner. And we'll talk more about that later in the course. But there are 2 types that we'll talk about here. One is gamma radiation. That's emitted by the nucleus of a radioactive atom. And then X-ray radiation is emitted by the orbitals or shells of an atom. So the concern about radiation is that it is damaging to cells. Again, it can damage genetic material, it can damage structures within a cell, and ultimately kill the cell and ultimately kill the organism. Now, ionizing radiation is also just a term for most of these types of radiation because they can actually cause an atom to take on a charge, and a charged particle is known as an ion. Okay, now what really defines the chemical characteristics of an organism is not so much the nucleus, but it's really the distribution of electrons. And so again, we're going to be looking at electrons as being distributed in concentric shells, so-called concentric shells moving away from the atom. But again, the actual orientation is much more complex than that. And generally speaking, electrons that are held close to the nucleus have less energy than electrons that are further away from the nucleus. But we'll talk more about that at a later time as well. Now, the distribution of the electrons then, we're going to be looking at, as I mentioned, in concentric circles around the nucleus. It's not really that realistic, but it will work because I certainly can't draw, and it's easier to visualize as well. And it also explains the behavior of the atoms. So when we look at these orbitals or shells, we'll just be numbering them from the inside out, so shell 1, shell 2, shell 3. And there's a certain number of electrons that each shell will hold. Not all shells will hold the same number of electrons. And so we're going to look at a formula here in a second, but for example, the first shell will hold a maximum of 2 electrons. The second shell will hold a maximum of 8 electrons. And the third shell will hold a maximum of 18 electrons. And then it keeps increasing as we go further out. So let's look at this. And again, the formula that determines how many electrons that will fit into a particular shell is 2n to the second power, where n represents the number of the shell that we're looking at. So if you look at the first shell, we would substitute the number 1 for the n. And so 1 squared is 1, 2 times 1 is 2. So the first shell holds a maximum of 2 electrons. So if an atom has more than 2 electrons, then they need to go into another orbital. They would have to go into the second shell. The second shell, again, if we plug the number 2 for the second shell into our formula, we find out that the second shell will hold a maximum of 8 electrons. So if an atom has more than 10 electrons, they have to go into another orbital or shell further away from the nucleus. The third shell, again, if we substitute 3 in our formula, tells us that the third shell will hold a maximum of 18 electrons. Now, as we begin to move further out, it does get a little more complicated because there are subshells. So for example, in this third shell, there's a subshell of 8 and then another subshell of 10 outside of that. And that becomes significant when we look at the behavior of atoms, but I'll talk more about that in a few minutes. So as I mentioned, inner subshell of 8, outer subshell of 10 electrons. 4 shell will hold a maximum of 32 electrons, actually composed of 4 subshells of 8, actually. But again, we're not going to be going that far out, so we'll be working mostly in the first 3 shells. Now, generally, electrons fill from close to the nucleus away from the nucleus. There are some exceptions as we get further out, but again, we're going to be working primarily with the first 20 electrons. So when we look at the first 2, they go into the first shell, then the next 8 electrons in the second shell. The next 8 electrons will fill that inner subshell of the third shell, and then we jump out with 2 to the fourth shell before finishing the rest of that third shell. So we're not generally going to be working more than 20 electrons, but do notice that the first 18 fill from the inside out. Then we jump out to the fourth shell briefly before finishing off the third shell. Now, again, just to emphasize that the actual shells and orbitals have some very bizarre three-dimensional shapes that are, again, kind of beyond our coursework. So when we look at elements, we're going to be looking at shells as concentric circles. Okay, so what I'm going to do then is what I would like you to do is I'm going to tell you what elements we're going to be considering. I'm going to give you the atomic number and the mass number. And I would like you to try to draw those atoms, the electron distributions, and the number of protons and neutrons in each nucleus. So the first 2 that we're going to be considering are hydrogen and sodium. Hydrogen is atomic number 1, and it has a mass of 1. Sodium is atomic number 11, and it has a mass of 23 Daltons. So let's go ahead, and again, what I would advise is actually stopping the lesson or module at this point and trying to draw those and then seeing if you've done them properly. But let's go ahead and look at those electron distributions. Okay, so what we're going to work with is an assumption that we're always going to start with the same number of electrons as protons. So we're going to assume that these particles are electrically neutral. So in the case of hydrogen, it was atomic number 1, so that means it has 1 proton. It has a mass of 1, which means it has 0 neutrons. And so we're going to assume that if there's 1 proton, that this atom has only 1 electron. So the only electron then would go into the only orbital, and this essentially would be the structure of that atom. Now, sodium has 11 protons. Again, its mass was 23, so 12 neutrons. And we would work on the assumption that there are also 11 electrons. So the first 2 would go into the first shell. Now, again, there's 11 electrons to work with, but this first orbital only holds a maximum of 2. So that means the next 8 have to go into the second orbital. So the next 8 would go into the second orbital, and then we would still have 1 left over, and that's going to go into our third orbital. So one of the things that I want you to notice is that both hydrogen and sodium have 1 electron in the outermost shell. And that's significant because what determines the behavior of atoms is the outermost shell. Atoms that have full shells do not tend to react with other atoms. In other words, they will not form chemical bonds. So if we look at both hydrogen and sodium, are the electron shells full? And the answer is no. This shell will hold a maximum of 2 electrons. It's only got 1. This shell will hold a maximum of 8. It's a subshell, actually. You may recall that first subshell will hold a maximum of 8. So in both of these cases, hydrogen could either gain 1 electron or lose 1 electron. It tends to lose an electron to other atoms. Sodium could either gain 7 or lose 1. It tends to lose this electron, leaving a full shell underneath. So since the shells are not full, these are chemically reactive substances. Also, what I want you to notice about them is that both hydrogen and sodium are in the same column on our periodic table. So they're in the same chemical family. And as it turns out, all of these elements all have 1 electron in the outermost shell. So chemically, they will tend to behave in a similar way because they all have only a single electron in the outermost shell. Okay, now the next two elements, calcium is element number 20 with a mass of 40 Daltons, and magnesium is element number 12 with a mass of 24. So again, I would encourage you to stop the video and draw those out, and then we'll see how they look. And let's go ahead and take a look at that. So again, we would have 20 protons in the nucleus, 20 neutrons. If we assume 20 protons, we would also assume 20 electrons. So the first 2 go into the first orbital, the next 8 will go into the second orbital. It will only hold a maximum of 8. You may recall that the next 8 go into the third subshell, and then we have 2 left over, so they're going to go into that fourth shell. So 2 electrons in the outermost shell. Magnesium, atomic number 12, so 12 protons. It also has 12 neutrons in the nucleus, and we would assume 12 electrons. So 2 in the first orbital, because it's all it will hold. The next 8 in the second orbital, that's all it will hold. And the next 2 into the third orbital. So calcium and magnesium both have 2 electrons in their outermost shell. Is that shell full? The answer is no. Certainly here we have a subshell of 10 we still have to fill in, not to mention another subshell of 8. So these shells are not full. This shell is not full. Again, another 6 could be added here. So neither outer shell is full. And you'll notice that magnesium and calcium are in the same chemical family, along with beryllium, strontium, and others. So all of these will have 2 electrons in their outermost shell. They also tend to behave in a similar way chemically. That's why they're stacked vertically together. So those are the same chemical families. Okay, I didn't foreshadow here, but fluorine and chlorine. Fluorine is element number 9 with a mass of 19. Chlorine, element number 17 with a mass of 35. So again, element number 9, we're going to assume 9 electrons, so 2 into the first shell, the remaining 7 into the second shell. Chlorine, 17 protons, so we would assume 17 electrons, 2 in the first shell, 8 in the second shell, 7 in the outermost shell. Again, outer shells are not full, so these atoms are both chemically reactive. And not surprisingly, they're both in the same chemical family because they have 7 electrons in their outermost shell. Okay, then that leaves us with neon and argon. Neon is element number 10 with a mass of 20. Argon is element number 18 with a mass of 36. So let's see what those look like. And you'll notice here that element number 10 protons, 10 neutrons, so that would mean 10 electrons, 2 in the first shell, 8 in the second shell. Argon, 18 protons, so we'll assume 18 electrons, 2 in the first shell, 8 in the second shell, and then the third subshell is full. So what these two have in common is that the outer shell and subshell in this case are both full. So neon and argon are chemically non-reactive. They are not likely to react with other atoms because they don't have electrons to give away to fill shells, and they don't need electrons to fill shells. And again, not surprisingly, they are in the same chemical family. So all of the elements in this column then tend to have full outer shells or subshells and do not tend to be very reactive. So that outermost shell that determines the characteristics, chemical characteristics of an atom then we call the valence shell. And again, as we look at the periodic table then, what this does is give us an idea as to how they will behave chemically. So as I've already mentioned, hydrogen, lithium, and so on all have 1 electron in the outermost shell. They tend to want to give that away. If we were to compare that to fluorine and chlorine, they tend to have 7 electrons in the outermost shell, and they generally need 1 electron to fill outer shells. So by looking at whether electrons need to get rid of electrons or gain electrons, we can then begin to make predictions about whether there's going to be a chemical reaction occurring between these. But this is something we'll pursue in the future. So again, the organization of the periodic table then, chemical families tell us a lot about the behavior of different atoms, and the behavior of the atoms is determined by the electron distributions in the outermost shell. Now, one other thing I would like to go back to very quickly is that electromagnetic radiation that I mentioned earlier, gamma rays and X-rays. These are, again, types of radiation where particles will move in wave-like patterns. And one of the ways that we distinguish between electromagnetic radiation, different types of electromagnetic radiation then, would be the difference between the crests in these waves. And that's what's known as a wavelength. So one of the things that we'll come back to is that we will be looking at the electromagnetic spectrum. It not only includes gamma radiation and X-ray radiation, but it also includes things like visible light. And so what determines some of the behaviors of different types of electromagnetic radiation then is the wavelength, the length from the crest of one wave to the crest of another wave. And then wavelength in turn is related to frequency. So again, if we had some kind of measuring device over here, and these waves were moving past that measuring device, every time the crest of the wave passed this point, that could be measured. So the longer the wavelength, the slower the frequency, the shorter the wavelength, the greater the frequency. So there's a relationship between wavelength and frequency. So ideally now then, what you can do then is if you know the atomic mass and atomic number, you would know the makeup of the nucleus of an atom. You should be able to determine the electron distribution around the nucleus of the atom, and then also predict as to whether an atom is potentially chemically reactive or whether it's non-reactive. And where we're heading from this then is that we'll begin to look then at specific atoms. If we put them side by side, will they form chemical bonds with one another? That's what we ultimately want to decide. And chemical bonds then will involve either the transfer of electrons from one atom to another or a sharing of electrons between two atoms. So we will eventually be able to predict whether atoms are reactive in general and whether atoms will react with one another, and also whether they will transfer electrons or whether they are more likely to share electrons. So that's where we're headed, but we'll take care of that at another time.